For this video, I thought I'd do my best Viren impression. So today we want to talk about electrical circuits. In particular, we're going to give you kind of the intro, looking at electrical current and Ohm's law, which is the most important formula in basic DC circuits. So to start with, we're going to talk about electric current. If I was to talk to you about just current, like, current in a river, for example. And I was to ask you, hey, what is current, right? How might we define what the current is? And I think that what you would come to the conclusion is that if I'm looking at a river, so just like kind of a cross section of a river, right? That you'd say, well, isn't it the rate of flow of water? You say the current is the rate of flow of water. And if I asked you for units, right, you might say maybe I'd measure that flow in units of maybe, gallons of water per second or something flowing by. You say maybe I would go ahead and I would take a look at one spot, right? I'd look at like kind of a cross section here, right? Right, in the river, and I would sit there and I would watch it, right? And maybe I'd sit there with a little stopwatch, right? And I would go ahead and I would go click, and I'd watch all the water going by, water flowing. Stop the stopwatch and measure how much water flowed past that point in the river in that much time. And I'd say, oh, it was that many gallons per second, and that'd be my flow rate. So electric current is a flow rate. And again, I'm thinking about it in gallons per second. I'm not thinking about meters per second, right? I'm not thinking about a velocity as it goes down the stream, because if I had, a mighty river, right? Maybe the water in that mighty river, if it was flowing at the same speed, that's going to have a bigger and stronger current. There's more water per second flowing. Is the way I'm going to describe that. But when I talk about electric current, I'm going to think about the flow rate, not of water. I want to describe electrical current as the rate of flow of charge. And so I'm going to go ahead and I'm going to measure that. If you think about it, what units would you use? Well, if it's water, it's like in gallons of water per second. With charge, I want to think about coulombs of charge per second would probably be my units. Right? And so you say it's a rate. So I'm thinking about is charge over time, right? Charge per second. And so electrical current, the symbol for electrical current is going to be a capital I. I don't know why it's a capital I. There's no I in current, but that's the variable we use. So you'd say the current, you say, well, we want to have charge over time, but it's a rate, right? And so it's really going to be dq dt, okay, is my current. Now, if I wanted to, I could be looking at a wire, right? So a cross section of a wire, and I could be looking at all of those electrical charges flowing down that wire, right? You can say, oh, look, here's here's electrons flowing down the wire, right? Yeah. And maybe I go ahead and I set myself a little cross-sectional area here, right? And I'm going to go ahead, I'm going to watch that cross-section there, right? And I have my little stopwatch, and I go ahead and I keep track of time, and I look at how much charge goes by, right? Flowing through, stop, and I say in a second's time, how much charge went by that little cross-section per second. And that's going to be my rate of flow. But you say, well, what if I went ahead and I measured for, 10 seconds, click, and I let it run for 10 seconds and click, stop it, and I count how much charge went through. If I just take that total charge that went through and divide by the total time, then you say, well, gosh, if I take the total charge went by per time, that's not giving me the instantaneous current. That's actually just giving me an average current. You say, well, are there going to be cases where that current flowing down the wire is going to be changing with time? And so that, it might be fluctuating, a little more current, a little less current, a little more current. And if I did this trick with the stopwatch, I'd just be getting an average. You say, well, yeah, there are some cases where the current in the wire is going to be changing as time goes by. In particular, one that we talked about is when we go ahead and we take a look at charging up a capacitor. If I had a circuit and I'll go ahead and I set up my battery, right? And hook it up to a capacitor, right? And here, I'll show you a new circuit symbol. That's going to be a little line like this. That's a switch. See, I can like flip the switch closed to run the circuit, and flip it open to close the circuit. Circuit on, circuit off, right? It's a little switch. Anyway, if I go ahead, when I click it on, current is going to start to flow. Here I've got my low V side and my high V side, right? Mark of negative, positive. This is the low V. It's not actually charged. Again, a battery is neutral, but I've got a delta V there from one side to the other side of the battery. You say, when I do that, charges are going to start to flow. You say, well, what would happen is electrons would start to flow around counterclockwise in the circuit. And I'd start, once I close that switch, and electrons would get to this plate of the capacitor, right? And at the same time, electrons will start leaving this plate and coming to this side of the battery, and this side of the capacitor starts to charge up positively, right? And so you say, but as time goes on, this battery has to push more and more electrons to that plate. That plate's already charged negative. It's going to get harder and harder to push more electrons to that plate. And as this plate loses electrons, becomes more positive, it'll be harder and harder to pull more electrons away from that plate. And so the rate of flow in the circuit will be changing with time. And we'll take a look at this at the end of this unit, be looking at charging and discharging capacitors in a circuit. That's the last thing for the circuits unit. And so you say, so we're going to care about instantaneous flow as well as just a general average flow. Okay. Let's hear it. The other thing that I need to tell you about this is getting back to these units. You said the units are in coulombs per second. Well, that starts to get a little long to say. And so they developed a special unit for current. Electrical current is going to be measured in a unit that we're going to symbolize with a capital A. That unit is named after a French scientist named Ampere. Okay, but in America we don't pronounce don't give the French pronunciation. We don't say ampere, we say amperes, right? And in fact, we're pretty lazy, and so instead of calling them amperes, we usually just call it amps. Okay, so amps is the unit for electrical current. 1 amp is just a coulomb per second of charge flowing in the wire. But alas, there is one last thing I have to tell you about electrical current here, and that is, do you remember how charge, positive and negative charge, was originally defined by Ben Franklin? Do you remember that he had made the assumption that he had the glass and the silicon, he rubs the glass and the silicon, realizes charge is flowing from one to the other, but he can't tell which way the charge is flowing, so he makes an assumption that the charge is flowing to the glass, so it has extra charge. He said, okay, we'll say that's positive. And later on, they found out that the electrons, the little particles were electrons that were actually leaving the glass. Well, the only way the glass can become positive when the electrons are leaving it is if the electrons are negative. But this was not discovered for like 140 years after Franklin. So everyone was always assuming that the charges that were flowing in circuits were positive charges. And that is why, even though in this example circuit here, the electrons are flowing counterclockwise, we always define the current to be the direction that a positive charge would flow. So we would say the current is going clockwise in this circuit, even though it's really electrons flowing counterclockwise. So something very, very important to know is that the direction of the current is defined to be the direction of positive flow. The direction a positive charge would flow if it could. If, for example, I went ahead and I had a chunk of wire and I set up an electric field in that wire, right? I hook it up to a battery and it makes a voltage, makes a E field in the wire. In this case, my E field, say, is going this way, right? Okay, that's where the electric field's going. Then the little electrons are going to get pushed to the right. Okay, but for just a second, let's say this tube is not, in fact, a metal wire. Maybe this is actually like a hollow tube that's filled with an electrolytic solution. And so it can have positive ions going one way and negative ions being pulled the other way by that same E field. And so maybe there's some positive ions flowing this way. right? Then when I go to calculate my current, those two flows, negative to the right and positive to the left, will partly balance each other out. And that's the way I would calculate the current in that, right? And so if I had, 2 coulombs of positive charge flowing to the left every second, and I have 3 coulombs of negative charge flowing to the right every second, my total flow is going to be 1 coulomb of negative charge to the right each second, which means the current is 1 coulomb per second to the left. See if that makes sense. All right, then pause it, go back, listen to it, see if that math makes sense to you. All right, so moving on from there. I want to go ahead, if you're good with that definition of current, that's charge per second flowing in a wire, I want to go ahead and think about this a little bit more. We said that if I want to make current flow in a wire, then I'm going to need to have an E field pushing that charge along the wire, right? And you say, we also know that to have an E field, I'm going to have a voltage. You say, if I'm going to have an E field in wire going along the wire, there's going to be a delta V then along that wire, right? So the way I do that is typically provide a delta V is we're going to have a battery. So let's set up a little experiment, right? In this experiment, I'm going to go ahead and hook up a battery. Okay, I'm going to go ahead and just draw the picture of the battery instead of using the battery symbol this time, just because, right? Okay, and there's a little bumpy end. Yes, that's the positive end of the battery. That's the high voltage end, and here's the negative end of the battery, right? I'm going to go ahead and hook it up to the wire. And here I'm going to wire in an ammeter. We say, hey, what's an ammeter? Well, that's a device that measures current, measures the flow of charge in something. You say the current goes in one side of the ammeter, goes out the other side, and the ammeter counts the current, the charge flowing through. You say, well, look in that name, you'd say, well, you would think that a device that measures current would be called a currentometer or something. But instead they named it after the unit. And you say, well, wait a minute. I remember the original unit is amperes, which we call amperes, but we shortened it to amps. But even that was too long. We just dropped the P, and now it's just ammeter. And that's our device for measuring current. The symbol in a circuit diagram is an A in a circle. All right, anyway, we're going to go ahead and bring this over, right, and bring it back in. When we make that last connection, then current will start to flow in this circuit, right? My current is the direction a positive charge would go. A positive charge would go from high V to the low V side of the battery, so it would flow around this way. All right, and so I'm going to go ahead, I'm going to use the ammeter to measure that current that is flowing through the meter and back to the battery. And when I do that, I can then make a graph. Because I'm going to go ahead and swap out this battery, right? This battery which provides a delta V, right, from one side to the other side of the battery, right? I'm going to go ahead and swap it out, and I'll pick a battery now that has a different delta V, a different voltage, potential difference, and hook it up, and then see what the new current is. And then I'll swap that out, put in a new battery with a different potential difference, different delta V, and see what that is. And so I'll make a graph. Now, you would anticipate, hey, the variable that I'm changing and setting the value of is the delta V, and the one I'm measuring the effect on is the current, the I. So you would guess that I would do, delta V, the independent variable, on the horizontal axis, and the dependent, the current, on the y-axis. But for my own secret reasons, I'm going to flip it around the other way. So I'm going to put my delta V, right? That's my potential difference based on what size of battery I'm putting in. That would be measured in units of volts. On the vertical axis and on the horizontal axis, I'm going to go ahead and put in the current, which would be measured in units of amps. Right? So I'm going to go ahead and think about this now. We're kind of doing this as a thought experiment. Then you say, well, what should this graph look like? You say, well, let's start with kind of the extremes. What if I had set up a delta V of 0? I had basically no battery, right? And I touched the ends of the wire together. How much flow am I going to get in that wire? I'm not going to get anything. So we know this graph had better go through 0, 0, right? If I've got no delta V, I'm not going to get any charge flowing in that wire. right? And you say, well, as I go ahead and I hook up bigger and bigger batteries to it, larger potential differences, and delta V goes up, 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 up. You say, well, the current ought to increase, right? I'm going to get more than zero. I'm going to get some current flowing when I hook up the battery, right? And so it makes sense that it's going to go up. So we're expecting this graph to head off this way. But you say, now how is it going to go up? Maybe, right, as I increase the delta V, right, I'm going to get more current out, but maybe it kind of, peters out at some point. Or maybe it's hard to get it started flowing at first, but then it flows easier and easier as I put bigger delta V on it. Or, and at this point, everyone crosses their fingers and they hope that it's going to end up being just a linear graph, is what everyone kind of hopes for, right? Because linear graphs are easy to analyze, yeah? Well, it turns out that for many materials, the graph that you'll end up with is a linear. So this is in fact what we get for a lot of materials. Materials like that we're going to call ohmic materials. I'll define that a little bit more carefully later. But ohmic materials are materials that will give us a nice linear delta V versus I plot. And so you say, all right, if I got a straight line graph, I know how to mathematically model this. We're going to say this is a direct relationship. And I can do my math of magic here and do say y equals mx plus b. In this case, the variable on the vertical axis would be the potential difference. The variable on the horizontal axis would be the current. The vertical intercept is 0. It makes sense that if I've got no voltage, I should get no current. And so then I just have this slope to worry about here. And you say, okay, well, the way we usually figure out the meaning of a slope is we think about the units, right? And you say, okay, what are the units on this slope? And you say, well, the units for that slope, it would be measured in, well, we calculate as rise over run, right? So this would be measured in volts per amp. And so you say, well, this is saying, now we're going to write a for every statement. We'll say for every 1 amp of current that's going to flow in the circuit, I need to apply this many volts of potential difference. So it's like, so you say, what would happen if this graph, so you say the bigger that value gets, right? I'd have to have a bigger battery per amp of current I want to get to flow. And so the bigger that value gets, the harder it is to push charge through this circuit. So this is telling me something about this circuit, maybe something about the wires I've got hooked up here, about how difficult it is for charge to flow, right? And so what we're going to call this, we're going to give it the variable R for resistance. Okay? And that's going to be a measure of how difficult it is for charge to flow through a circuit. Actually, for charge to flow through any object, we could measure its resistance. Let's take a look at this graph just one more time real quick. Hey, what would happen if, what if this graph was steeper? What does that tell you about that circuit? Well, if it's steeper, you say, look, to get a certain amount of current out, look, I have to hook up this big of a battery, right? Whereas you say this, for that really steep one, you say on the other hand, if I had a circuit that gave me a graph like this, with a smaller slope, a smaller resistance, right? Then you say, look, for that same amount of current out, now I only have to hook up a battery that's this big, right? And so you say, so the steeper this graph, the harder it is to push charge through, the bigger battery you need. So you say, yeah, to get the same amount of current out. And so you say, so yeah, it makes sense. This slope of this graph is a measure of how difficult it is for charge to flow through. We call it resistance. So this formula, we're typically going to write this formula like this. We're going to say delta V is I times R. It's just traditional, right? I times R is the way I'm used to seeing it. This formula has a name. It's called Ohm's law, because the fellow who first mathematically proved this, his name was George Simon Ohm. Now, oftentimes you'll see Ohm's law written without the delta, because you remember back in the old days they couldn't type deltas on keyboards, so they used that other double subscript notation for it. But it really is the potential difference. It's the change in V from one side of the thing to the other side of the thing that you're measuring the resistance of. Okay, so it's the change in V from one side to the other side of the object that you're measuring the difficulty for the charge to flow through. Okay, and that's equal to I times R. Okay, this formula is the one that we use the most in analyzing simple circuits. You'll use it again and again. You'll use it to analyze like the circuit as a whole, or to analyze this part of the circuit, or just this particular object in the circuit. And you'll use Ohm's law over and over again while you're solving a DC circuit problem. Okay, the other thing that you need to know about Ohm's law is that the unit for resistance, right? We just calculate out it's going to be in volts per amp. Well, volts per amp is a little long to say, so we give that a special name. So a volt per amp, we call that an ohm. And so you say, well, gosh, how are we going to abbreviate ohms? Well, usually we use the first letter, but there's really good reasons not to use the first letter of ohm as an abbreviation, right? You wouldn't want to say that something has a current of 10 ohms, because that would look too much like 100. So instead, someone had the bright idea of, to symbolize ohms, to use the Greek letter capital omega, right? So that's the symbol we use for ohms. So I would say, hey, this thing has a current of 10 ohms.